Quack.
I want to do just a quick survey because I kind of want to tune what I'm going to say to who we have in the audience a little bit. So how many people here have at one point or another, whether it was your official job title or not, had to maintain data for an organization or group of people? Hands up. Oh my God, okay. So that's great because you will feel, you will be able to connect on the level of pain because I think that as a dominant emotion when maintaining data. Okay, so who has officially had a data engineer job title? Yeah. All right, so these are people who probably had control of budgets, or at least like some portion per budget. Okay, what about the other side, the consumers, like analysts, BI, gotcha, so people who were like stats, gotcha, so you had to deal with all the mess the first group of people were making. I've tried to be a data scientist several times in my career, and every single time I got there, I'm like, how can you work like this? And I just became a data engineer again, and so I finally gave up and became a full-time data engineer something like 10 years ago. So I arrived in New York, fresh face, and New York in 2009 was like magical for data. I know the technology was developed globally, Silicon Valley, West Coast, but in New York, the data got used like on the ground. We had finance, with a streets were full of quants. We had a ton of startups up and down Broadway. There were like Hadoop meetups every 2 weeks. There are a bunch of new data parks coming, and honestly, like, thank you guys for coming because I think it's coming back. Philly does a New York systems meetup group. Eric Zink does another database meetup group. And I know meetups got really crowded with all kinds of like spammy meetups, but I think like the data engine meetups are there. And I'd love to see what's happening again. So in that vein, I want to talk to you about like how I ended up with MotherDuck because it's an interesting story, and also I want to show you what we're doing there to make sure that what we build is actually like useful to our customers. Okay, so basically what happened is something like this. It's maybe all me, but the ex-people from these three database companies, for some reason knew me as a useful pain in the ass. And they said, come on, we're going to like make something new. And what they were proposing is like really appealing because an experience I had like 10 years earlier. And this was it. All right, so this is 2010. I'm working at an ad tech company. And at the time, 300 terabytes was a lot of data. The fact that we don't consider that as giant now is actually really something. We had the largest East Coast Hadoop cluster at the time. And the guy whose job it was left for Yahoo, the mother of all of Hadoop operators, and I got the job. And it was like, I was learning MapReduce. There was no SQL in Hadoop. There was no nothing. We just wrote everything in raw Java. And we didn't realize at the time, but there was like all the data engineers around that time, the first people in big data were becoming very bad database software writers. We reinvented consistency terribly. We reinvented partitioning terribly, but we got it done. And the reason we had to do it, the same reason Google had to do it, the margins on ad tech are really slim. You're talking like 1/10 of a penny per 1,000 impressions, and each one of those generates a log line. So where are your margins to pay Oracle $10,000 per core per month for whatever they're doing? So we were all desperate. We all got commodity boxes, and this was kind of like MapReduce, which was kind of the forerunner to a lot of the big data technologies that came after. So I was there, and I was like, okay, I took over some summary jobs that we had, and typically I would just run the Hadoop jar, my job.jar, nothing was there, no pig, no I, it was all just Java. I did 42 seconds. And I thought, well, it's not like that much data, right? I could fit it on it took a few minutes, but I got over to my local, and I ran it, and I just like piped them, right? So I ran my Java and put it on intermediate. This is just on the console. And the thing ran in 4 seconds. And I'm like, is Hadoop a scam? Like, where are the other 38 seconds going? What's it doing? So what is it doing? Well, distributed systems have a lot of overhead. You basically have to like coordinate. First of all, you have to send data. So let me just think, if I want to send something to Stephanie across a network, I've got to serialize it, even before anything. So that goes into a buffer. Then that gets streamed up by the operating system, packet by packet, across the network. On the other side, that goes into another buffer, so nothing happened in the middle. could be delays. She has to reserialize it. So the data is being copied like 4 times on each side before she can see, hello, step. And that happens between all the stages of your job. And where does this happen? So let's just keep our computation to like SQL. The operators that require this shuffling across will be like hash joint, so anything that is a hash aggregate, anything that is a sort, so window functions are basically sorts these days. Any distinct operation, basically anything useful has to shuffle. Let me just actually skip to this for a second. I'll come back. So we have this like shuffle operation that's happening in broadcasting. These are the operators that use them. And on distributed systems, they do something like this. You have your partitions, which are given by each node. Then each of them writes, locally to a partition file, kind of locally, and then sends it across the network. You have this end-to-end, like, crazy communications. You ever looked at a network graph during the shuffle operations of the distributed system? Quiet, quiet, and then the first start producing in this network storm where everyone, the second part of the plan cannot proceed until this thing knows it's got all the green sections, which could have originated on anything over here. And so you're exposed to long tail latency. So of course, if you have to do this, you have to do this. This is what enabled you to run a query over 300 terabytes data for like a few dollars. But my God, for smaller data sizes, this is absolutely insane. I get a sense the entire file from here to here complete in 1/10 of the time it took to do this kind of shuffle of dance. So basically, we kind of like, in order to enable the top 1% of queries, we pay this distributed systems overhead for everything else. I don't want to talk about the social reasons, right? Everyone tried to like, oh, we're Google, we need MapReduce. But I was at companies where it happened, where we easily could have run on smaller systems. But there was incentive from the top to make sure that they participated in big data. There's a lot of like, we got to have this technology too, everyone else does. Oh yeah, so I want to compare that to what happens when you just have something you can process. Okay, so this is the process on your computer. You can do a lot of parallelism on one machine right now, not even like time shifting. You have so many cores. We'll get to why in a second. So same query, we're gonna group over here, but instead of like sending across a network, we're just gonna like write to buffers in memory, and we're gonna like locate them and create little mini partitions. These will be the other side, what previously was on the bottom, and these just have pointers to the relevant sections. There's no copying here. My output went straight to what my readers were going to read. And so I've accomplished the exact same thing as with the shuffle, except I haven't copied a single thing. My output is coming input directly. Now you couldn't do this in 2010. 4-core machines were a lecture farm, maybe 8-core machines were a lecture in 2010. But we have nowhere left to go for all the transistors that TSMC managed to train on, except create more cores. And so this makes a lot of sense. Broadcasts, where, for example, you're doing a join for a small table to a large table, and that small table needs to be everywhere, assuming you don't have it already co-located on the storage of those nodes, this is even worse. Just like in the single node case, well, everyone just points to the same block of data. And over here, I need to copy this to all these machines redundantly. So why did this happen? And let me go back to some economics here. So this, if you're working technology, then your kind of career is somewhat based on material science. Basically, stuff happens in labs where new chemical processes for etching show up. They take 10 years or 15 years to go through the kind of pipeline and eventually show up in a fab. This process becomes so intense that only a few companies in the world can do leading-edge nodes. But not all the qualities scale linearly. So this is the free lunch is over. This is the end of computing progress for free. Somewhere around the time that I started getting into ad tech and doing all these computations, frequencies stopped. I know you could buy a 3 gigahertz machine at one point, but basically we kind of decided that 2 to 2.5 up to 2.8 is the ideal kind of cooling. Everything after that, things became too hot. Transistor count continued to go up because we kept on able to shrink it, and miraculously they're still able to kind of shrink it. We'll see how much longer. So where did all these extra transistors go? They didn't go, we couldn't have anything hotter. We were getting too hot to cool, so our watts stayed the same. Our single threaded performance didn't get any better because we basically, these algorithms got perfected over here, and so they kind of just froze the frequency. They all went to more cores. So this is the only line that goes up here. So we now have machines with 64 cores. We're used to have 4, but they're no faster when they load to 4. So let's look at what your money got you. I tried to find on history, what $1.25 an hour roughly bought you in 2014, and this is what came up on Amazon. So of course it's 3 times the cost of what you could get if you like cream medium data center. 8 cores, cache sizes are okay. 68 gigs RAM, it's not bad, but look at the bandwidth. Aggregate bandwidth to your machine is 51 gigabytes per second. A Graviton free at $1.30 an hour has 300 gigabytes of sapping the bandwidth of your machines. That's as fast as your high-end networks used to be if you were lucky. So if I have 32 cores and have 300 gigs bandwidth in between, and I add $1 an hour by skipping once that day, and I get a 3 terabyte SSD for caching. Doesn't this look a lot like a mid-sized Hadoop cluster from 2010? And suddenly all those shuffles go away, and we start to just kind of hand people pointers. If you felt like the machines you're doing, the systems you're working with were getting really heavy, and you're going, well, technology's advanced, how come I'm not seeing my job? It's this is why. You can do much more in a single core than you ever could. But none of the software that was around really has been taking advantage of it. There weren't incentives. The big data companies wanted to sell you more and more. The cloud companies wanted to use more and more nodes. So who was incentivized to make something efficient that could do this? So actually, I'll just tell you a little bit about how DuckDB came to be. Okay, Hannes will tell you the better version of the story. Hannes Nielsen. But as I understand it, he was walking by a couple of people who were doing some R or Pandas work, and they're doing some data transformational steps. And I don't know if you've worked in Pandas, you do dot transform, dot filter, dot whatever, and it materializes in memory after every step, which is insane to a database person. Why would you materialize your entire matrix, your whole data set after every operation? You would pipeline. Otherwise, you're going to get a data size, essentially double your data. Wes McKinney, I think, said that the recommended amount of memory is 5 to 8x your data set to properly run Pandas. Well, nobody does that. They kind of just make it work and they spill like heck. But the way DuckDB came around was just the insanity of that wasteful copying as the data sets got larger and applying essentially cutting-edge research as far as pipelining data and parallelizing operators to a market segment that basically the large companies had ignored, which is how much analysis can you do on your computer? Your local machines these days, doesn't matter what platform you are miracles of technology that you would have paid $50,000 for 10 years ago, and you just have it there. So DuckDB is basically the state-of-the-art for analytic processing stuck into a library. So this came from, what I got up here is actually a blog post that our CEO put up. In this, I don't know if you saw Redshift put a paper out, including an attached data set. So if you ever used Redshift, you got these stats tables that tell you kind of okay, I ran this query, how much did it scan, whatever. So they sub-aggregated that across a bunch of customers. And one thing you could extract from there are people's data sizes and people's scan sizes. So when you look at actually, and this is a 3-month period, about 500 million queries they sampled. I can't add it, these are too complicated. So if I add up from here, these are query sizes, and session will be kind of the session time, it's about 4 or 5. 95% are underneath 10 terabytes of scans. If we lop up this 5, 90% are under 1 terabyte of scan. These are clusters, these aren't individual machines. So how many people are actually, 30% are 1 gigabyte, and still we're using these the same distributed systems for these queries as these queries. So you're well, maybe people just have a lot of data. The same thing happens, look how many people have 1 to 10 gigabytes of data on Redshift. The machine they're using to upload, their own computer could handle that data set just fine. And yet we have 10% of Redshift customers spinning up an entire cluster for them. There's a reason for that. It's hard to share data from your computer. So there are benefits to having a shared state. But clearly, I think people are overbuying relative to what you can go get one big machine for. And I think people are waking up to this. I love interruptions. I need them to keep me on track. Does somebody have any questions before I go on? Yeah, Emily. All right, we talked, so basically all that was like the motivation for why an opportunity showed up for DuckDB, and then turned why, being by the means of the car. So I've always had this feeling that we've been over-barning, using overly complicated systems for essentially over mostly source and aggregations, right? But DuckDB is not a data warehouse, right? In fact, it's really DuckDB is a library, and it happens to come with a CLI. They actually took the one from SQLite and started modifying it. But that's what you're running when you type in DuckDB. But what are the properties of this library? Well, first of all, you open up, runs the process, it locks the file. Can't have any other writers to it. You can't even have other readers to it while you have a write block on it. You can have 2 read blocks. It's local only on your computer. There's no network interface, there's no query interface. There's no users, obviously. It's only on local disk. All this, I guess, changed recently with like an S3 days path. And if you put it on EC2, you are paying for the entire time that it's up, whether you're like running it or not. The bar has been raised so high by Snowflake and Redshift and BigQuery too, especially on like what we expect from our data warehouses. But this is, you say you want a data warehouse, this is kind of like the minimum. So let's contrast that here. In order to like make something useful, okay, so I can do these computations, but unless I can share them with others, meaning other people can query them, it's not much good sitting on the laptop, and they're not going to expose my laptop. So we need multiple users to be able to query it. Also, they're not all processed on my computer. They have to, go across the network. Then I need some notion of identity, because we're going to be able to like make sure not everyone can do it. Probably the SQL UI. When I started, the SQL UIs on the web, everyone's using Databricks or whatever. They are so good, like Snowflakes and BigQuery's, like SQL editors. You can sit there and work 8 hours a day now. So you need a good UI. And these days, you don't just need a database, right? There are a lot of data teams out there which have like, they don't build their ETL from scratch. There's been a labor shortage. You could not get data engineers. There are a lot of companies which just couldn't justify it, full-time data engineers, or divisions of companies, frequently marketing divisions, right? They wouldn't be like attached to the name kind of labor pool, and they would be like, okay, we need to ingest this Google Analytics data, whatever, and a whole tree, a whole forest of SaaS companies showed up to kind of like do data processing for you. So with a credit card and some partners, you can get your data loaded, transformed, cleaned, whatever. And so you need that. That's table stakes now. You need a good, system of partners. Elena, sitting back there, raise your hand.
And not handling at all.
Yeah, is someone in charge of this. So if you have a beloved partner who you want MotherDuck to talk to, she's the person to talk to. So you need transport and query results. This is actually non-trivial. The Postgres interface is used a lot, but it's really inefficient for large data. It doesn't do any compression. It sends your data back for ORs. Snowflake's interface will determine if you have like more than, it's like 10 megs of data, and if you have more than 10 megs, it'll actually send it to S3, and your local client will just automatically patch there. People are used to the speed ups that these kind of like mechanisms have provided. They're also used to like either automatic scale up or pay only for what you use. Either way, they don't want to pay for things that they're not doing. They also want a file system that's not going to die if your computer gets trashed. And way easier uploads than just pushing things to like S3 and sending a copy command. So there's a big gap between like what you're going to end up with. So I really encourage people to try to build their data systems on DuckDB. The ecosystems of experimentation out there is like wonderful. We thought that there's a big opportunity to try to like solve these problems for a bunch of people, but still keeping the pricing aggressive enough that like the difference between what you pay with us and what you do with your DIY is small enough that you kind of go, well, let me just try it the easy way for now. So if you're going to do this, this is what you end up with. And there's one like kind of unique thing I want to point out. Okay, so this is all bog standard for anybody creating an open source project on the web. Containers, on some kind of form of shared storage, load balancer authentication. Basically every SaaS kind of looks like this. But with databases, there's a, can you still hear me?
think you press the button or something.
Oh man. We know it's out of battery. We can tell you.
Are you ready? No. I got the old again. Okay. So you have some kind of shared storage, and you're running some process. This is a database, but it's basically just DuckDB. We put a service layer in front of DuckDB, as you might. It started with gRPC. We've elaborated it since. But there's one really unique thing about this architecture diagram that you're not going to see in basically any other database out there. We do not have a client that is standalone that you import into whatever you're doing. We're an extension on top of DuckDB. And that means that any DuckDB user, the thing we want to provide is the illusion that you have this giant, powerful backend on demand locally, meaning that you're working locally. And there's this focus on, even psychologically, that you are always in control of the situation. You're not like begging some server to, please, server, complete my request in under 10 seconds, and I'll just wait patiently for you. We want you to be able to like intermix local and remote work kind of very fluidly. And so the experience we try to provide is that you're just working with DuckDB, it's just that these other tables happen to be like remote catalogs. So we do this thing where like you can actually.
Question.
Oh yeah.
Sorry, the previous slide before you move on, I just had a quick question on that. I saw that you had on the web UI for the web browser, this DuckDB WASM in there.
Yeah.
Is that implying that the hybrid querying works on the MotherDuck UI itself?
I mean, it's not us that's stopping that, it's browser security, right? So yeah, hybrid, but attached to what files? Like, so yes, so I mean, there is a file system inside WASM, right? And so like our load, if you look at our add files thing, it actually loads into the WASM file system, which by the way is a key value store, it's not even a tree.
Yeah.
So yeah, it does work. You can do it, the problem is like it has no access to your file system. And I don't think we're getting around that because I don't think the browser people are going to be ready for the kind of security nightmare as it would be if WASM applications could actually go local drive. I think like, I don't know, we don't have any front-end people here. There are some controlled attempts to make that happen because that would love to happen. It may be that like everybody else, we have to make an Electron app, and we'll see. We'll see where that goes. But it's a security thing. It's definitely not WASM's fault. Okay, so Stephanie knows all about this because she works on the database team. So basically, normal databases like DuckDB do something fairly. These are the phases of how your queries get executed. You hand it a string with a bunch of text. It gets parsed into tokens and turned into a syntax tree and then to a logical plan. At that point, you have all these names of tables. Those have to turn into locations of data somewhere. That's called the binding phase. So basically it locates table T1 and says, well, that's actually stored in this kind of location on disk. Then optimize basically says, okay, I'm a database, I'm really smart, I can figure out a much better way to do that query than you can, so rewrite your plain several times. And they're so good we basically rely on them. And then executes, which is actually in some ways the easiest part of this. We took the hard route. It would have been much easier if we had built clients that did like every other database, send a text, get that result. But because we want to preserve this like illusion of local experience, we actually do this like combined planning phase. So what we do is we cache your remote DuckDB catalog. So all your planning and binding actually works locally. So if you don't have a table name, you gotta get a table name that's wrong, you'll catch that locally with no top of the server. But if you make it past that much, then we'll start collaboratively optimizing. And the reason for that is we have to figure out what parts of your query can run remotely and locally. So the way that looks, so check out this crazy query. So this is the logic plan, let's say. The physical plan is basically a template board in this case. And we have two remote tables, which we're going to join together. And then we have a local table, which we're going to join against that. And then we're going to push the whole thing out remote. So this is a double round trip. So when our planner runs, basically it says, okay, what has to run where? We know that this table, this remote 1 and remote 2 are remote because in catalog says that. So this has to be remote. Well, what has to be local? Well, local 1 is a local file. the MotherDuck doesn't know that. That has to be local. So at that point, we basically have 3 nodes here that have to be run wherever they're going to run, and then we can color, one either local or remote, based on what makes more sense, where these operators run. So at this point, we've split the plan up into 3 subtrees. There's this subtree, which we decided is remote. That's going to join to this local subtree, and that's actually going to push the tuples all the way back to the create table as. This happens like transparently. You just write this query without caring kind of where the data lives. And we figure out all the mechanics of shuffling data back and forth wherever they need to remove tuples. And this is kind of to extend the illusion of like, I can use everything locally, but when I need like a big server access to large data, I just add the from. There's no downloading into compiles or no push into S3. It all just like happens as if it's as if you have MotherDuck working locally. So I'll show you practically how I use this. So this is one of my ELT jobs. So note this thing. This is a pandas data frame, which this probably came from, where did this came from? This came from like a bunch of JSON files, which I had to like parse in JSON. So it's actually a bunch of divs. That's in a pandas data frame. So let's look at this query. So we're going to insert into, this is a remote table, trusting. I'm going to select star here, but I'm going to replace one of my columns if, like there's an if condition based on a remote table. So this current user is not local, this is sitting on MotherDuck. This data frame is local, so based on this, I'm going to alter this, and I can insert the stuff remotely. And did you notice this magic thing? I can select from DF mentors. It's not us, right? This is like DuckDB Python magic. Basically, the DuckDB Python library, if it can't find a table, it will actually probe the local variables in scope to see if there's a name of a data frame in scope and bind to that. This is amazing for ETLs. Notice I didn't have to push that into a file, no creation of Snowflake stages or nothing. It's just an insert statement which could run locally, but kind of just joins the data wherever it needs to make it happen. So this anti-join, and it would have been a 3-stage job if I couldn't have like hybrid execution. And that's what we call it. Okay. So that's basically the pitch on like why MotherDuck came to be. What are the like technical conditions we gave rise to single node, something that, and then like our architecture where we try to preserve the local experience, and with all of kind of DuckDB's excellent UX. But I basically from day one have been trying to build against MotherDuck like you would if you like joined on our GA. And it was not ready when I first got there. A lot of things like, did not work that smoothly when I first started. But that's like, better I run into it than you run into it, And so there's this kind of like pushing the boundaries like 6 months ahead of where customers are to pave the way so that it kind of works when people kind of get there. Because when you just slap a gRPC interface onto DuckDB, and you start doing all this chicanery with high plans, there are a lot of edge cases being discovered. So why dogfood? Well, it would be hypocritical to not use the product that we recommend you use ourselves. So we just have to like put us in the same risk position. There's a lot of good incentives there. The other thing is like testing. Like when people don't have an imagination for what can go wrong, and they often like test the areas which are well lit. There's an infinite number of things you could test, but testing the golden path that users are going to use based on real use workloads ensures that at the very least these common things, they're going to be roughed out. Other thing is like a design thing. When you design a feature, it's not done when you release. It's done like 3 years later after you got all the feedback from how you were wrong in the design in the first place. And so by kind of putting dogfooding in the critical path on our early releases, we could actually see if the things we want to build were as ergonomic as we expected them to be. Another one which is a little more, I think like dentist equipment at this point. Not many people who design the tools for your dentist users are dentists themselves. Not every dentist becomes like a technician. And so there's kind of this like difference between what puts you in a position to write databases from using databases. And so there's this experience gap. So having somebody who has like the customer profile on staff really shortens like the iteration loop when it comes to, I'll give you an example. A lot of engineers think queries are like, so insert into X, these 4 values. But I've worked with DBT. My queries are 1,300 lines long. I've been passed through 4 people, 3 of which no longer work there, and everyone's afraid to touch because SQL is hard to test. They have 17 CTEs, 7 subqueries, so you put that in front of a database engineer, like, oh, that's what people are writing these days? I have no idea. It shows up. You can also feature flag. So we rolled a feature called differential storage. DuckDB thinks it's using an actual file system. Sneakily, we never delete anything. And this allows us to implement time travel by basically kind of giving DuckDB the illusion of the file system at any given point in time. So risky feature to roll out to replace the file system from underneath. We literally just nailed it. And so basically they enabled it for me, sort of like a month and a half, and then I verified that I could run our stack on it, and for the most part it went actually pretty smoothly. Another thing is that there's a good place to do customer repos. Having an environment that actually is similarly set up to customers, you can often recreate the issues they have, except unlike customers, you can attach your debugger to me, I won't complain. You can abort my queries, I won't complain. And so having kind of a high fidelity environment that's always running, I think has been useful. Also, I give more typical kind of data shapes. It's not going to be 100 rows, it's going to be 2 billion rows. It's not going to be 30 columns, it's going to be 400 columns with 17 nested things in there. And so it's, you want to anticipate things that are much closer. And of course, partner integrations. Because we run a stack that we actually use, we can go to our partners and say, hey, we'd like to try your BI tool, your transform tool on our actual data. And again, the incentives are really aligned. It's frustrating for us to work with a partner, it'll be frustrating for you with a partner. So it's a fairly simple stack, Airflow scheduler. At the beginning, mostly just Python. I brought in DBT when that seemed mature enough, and I'm expanding to use kind of Airbytes and some kind of partners. It's the kind of stack I'd set up any kind of mid-sized company that has digital ingest. And we're up to about 6,000 queries a day in 40 scheduled jobs. So it's a significant enough thing that you can feel confident that this is not some half-baked thing that nobody uses. We are probably one of the larger users of MotherDuck, at least on not a data volume perspective, but on a variety of query perspective. That's what I just said. Oh yeah, I calculate what I would have paid if I had to, and I do this, and so note the data volumes here. I type my data sets very tightly. I don't have these unstructured JSON fields everywhere. And that allows me to use floats, ints a lot. I keep my strings to kind of a minimum, because I know that vector execution engine really loves storing a type field. So I have half a terabyte. But in my old days, that would have been 10 terabytes, and that doesn't sound like a bit query. By doing a bit of this type discipline, knowing that I can always reload from log from S3, because it's really easy for DuckDB to hit S3, I can always recast and reflow it back up. But it means this is what it costs me. Our billing is ridiculously tight. We bill basically the integral under top. If you ran top and watch the bars go back and forth, we bill on the green stuff. And that means you only pay for when your query is actively working on something. Even when it's blocked on I/O, that doesn't seem to actually make it into our current pricing model. And so it's ridiculously cheap to run because we have to compete against DuckDB in some ways. We got to make it the DuckDB experience, that we can charge a premium on it, lower than other warehouses. And so if you follow discipline, you will get an really cost-effective solution through your data. And this is just a bit of profile of what Duckfooding has been since we started. When we first started, there was a question of this thing is going to work at all. And most of the time, I was just making sure that the basic stuff, loading data, a few aggregations worked. That's the golden stuff. I'll call it golden path testing. Over time, then we started getting customers. So certain portions of time became customer repros. And then we have this environment where we could load a similar data set and watch the logs happen in real time as I try to release. Notice that the green stuff, which are internal use cases, are minimal at this point because, I mean, there's no sense analyzing customer data when your golden path is like still full of like problems. Now, right around maybe 6 months before beta, the product got like significantly better, especially with every major DuckDB release. And I started actually to give feedback into like the usability of products. So they work, but were they in the right shape for like how people would properly use them? And it was still early enough in the product cycle that I could use my daily experience to inform how much to build. Then we get to beta, but this time the golden path is actually really good. There were like a few caveats that we sent as warning, but basic analytic workloads work reasonably well with a few things you have to kind of like work with. And at this point, now I'm actually doing work for the company itself. I'm the data engineer responsible for the analytics for the company. Still only 50% though. Then we get to our GA, which is just this year, and now maybe like 2/3 of my time is actually doing data for the company because the thing's not like giving me trouble anymore. And the reason is that all this work in the yellow area kind of quash these bugs kind of like earlier. So you won't be as surprised as if this works kind of stuff. So over time, I'll just become a data engineer again instead of a QA engineer. Yeah, and we have this pretty tight feedback loop. So I run an Airflow job. I can watch the logs in Datadog kind of like spin by. And it allows us, because with a customer, we'd have to say, oh, can you please run this thing? We're going to watch it. Or can we have access to your data for repro? We can never repro our customer data without like some permission or exchange. Your data is very private. And so having this like tight feedback loop between kind of like repro and internal logs allows us to like kill bugs a bit quicker. And so these are examples of the kind of issues which maybe wouldn't have been caught in testing but got caught in dogfooding. It turns out there's a slow leak of connections, file descriptors. It would accumulate over like a week, and then it would hit a limit at 1,000, and your backend would die. You'd never see it in unit test because you wouldn't run this slow leak over time. Concurrency and changes. It was thought that like alters were like rare events. They didn't know about DDT. Every materialization equals table is a create table as. Create is a DDL statement. And so we had this thing where like if the schema changed, your query would abort. If alters and catalog changes are rare events, that's fine, but this is not a rare event. So every time I ran my DDT jobs, it would abort other queries. So we killed that. Oh yeah, line SQL. So we have a SQL notebook. So errors would show up below your SQL. Well, that's fine if your like query's this big. If query's this big, then you're scrolling back up and down every time you get to an error. So we've recently moved to highlighting errors in line. Because with big SQL, that's what you need. It's what DataGrid does, that little red thing at the left. And it's what I wish, honestly, like Jupyter Notebooks would use. I told you about validating different storage. Oh yeah, bind time. So you can attach DuckDB to so many things. So if you attach it to your client, so you can do this. I'm going to attach to my own Postgres database. I'm going to attach it, run a query there, pipe it through my local client, join it with some remote data, and write that to a new table in MotherDuck. Notice we haven't attached MotherDuck to Postgres, your client has. So the problem is, we expect at least a row every 15 seconds to keep that connection fresh. If you write a highly selected query where you're scanning a billion rows and 40 come out over 10 minutes, because it's a full table scan, that actually timed out. And that's the kind of thing that it's really hard to test for. It's a very specific circumstance, but when we try that, over Postgres, it happened. Deepliness the JSON. DuckDB had an issue where, well, they thought, well, the JSON is what? 30 things, maybe one nesting level. And I showed up with something that was 80 levels in for each one record because it was a download from Mongo or a download from like an API which just had a document stored behind it. And DuckDB is not expecting that. So like 500 times the memory usage of the string just to parse the string. So that got quashed. And then slow extension load times. We were watching like the size of our binary, and that thing gets checksums and against the signed key for security. So every time you load an extension to DuckDB, it's extremely secure. But our binary has grown over time. We just weren't keeping track of like the amount of symbols in it, and it's taking like a second and a half. That's very noticeable when you run the stack that loads your extension that kind of time to the end. So I don't need including slide. Basically, that's what I've been doing kind of since day one, being essentially the sacrificial data engineer, your proxy, internally, trying to like run into issues before you do, which means that it's ready for you to try it. You can find me on the community stock. I'm Nicholas Ursa today, and I'm anxious to hear of your experiences. Any questions?